Welcome back to Allen High School's discussion of states of matter and solutions at the APIB level. Right now we are focusing on cleaning up a handful of new topics and then reviewing and tying it all together so that we can pull together the concept that structure determines function. So we'll be going back to our discussion, our understanding of bonding, and we're going to use how molecules behave in terms of gas laws and link that all finally together with a discussion of intermolecular forces. So bonding, we'll look at solids, conductivity, the whole variety of things all tied together. What we're going to look at first here, we're going to answer a couple of AP questions or AP-like questions. Some have been altered. So from the standpoint of kinetic molecular theory, briefly discuss the properties of gas molecules that cause deviations from ideal behavior. Now, in kinetic molecular theory, there were 5 premises, such as gas molecules move in random straight line paths, that temperature is a measure of the average kinetic energy, and so forth. The 2 that cause deviations the most are the fact that molecules truly do have a molecular volume. If the volume of the container is sufficiently large, it appears as if relative to the container, the molecules have no volume. But the reality is they do. The analogy would be the volume taken up by my body in Allen High School is pretty negligible because Allen High School is pretty massive. But if you narrow that now down to the volume defined by my classroom, my volume starts to have some significance there. And so that's one of the key ones, that molecules do have a finite volume. I mean, they're matter. All matter has mass and takes up space. But now what we're talking about is a volume that can become significant compared to the container. And this is especially true for large molecules and when we have a large number of molecules in a very small volume. So those would be the types of situations. So if you have a lot of molecules in a small volume, you're very likely to have a high pressure, right? Now, the next one is that kinetic molecular theory says that molecules experience no attractive primarily intermolecular forces if we're talking about gases. And you know what? That's simply not true. Many molecules do experience significant intermolecular forces. All right, now those intermolecular forces become more significant at very low temperatures. Molecules are moving very slowly with a low kinetic energy and can start to sense those intermolecular forces. So if Denzel Washington's in a real hurry and he totally runs by me as fast as he can, he's not likely to sense how amazingly beautiful and intelligent I am. But if we lower the temperature and slow him down a little bit and he's able to take a glance over, well, you know what they say. All right. So that's one of the things. Now, they start to experience significant intermolecular forces under high pressure. Under high pressure, molecules are typically packed closer together, and the closer they are together, the more they experience those intermolecular forces. Okay, let's take a look at B. I spent a little bit more time on that than I intended, but hopefully that gives you a fair idea of that question because I think it's a very important question. Okay, so given that, which of the following gases shows the greatest deviation? So based on size alone, this one, size is related to molar mass, but it's not equivalent. All right, size has to do, with how things are bent and shaped and the electron density. So size, though, can give you a good ballpark. And since carbon's, relatively small, a molar mass of 12.01, which means it's, got a few number of electrons taking up space with that hydrogen. So let's call that 16-ish. This is 32 plus 32. We're looking at 64. This is 32 and this is 2. Okay, so based on size criterion, we would think that it would be SO2 would be deviate the most based on size and taking up some amount of molecular volume. SO2 would be the most deviant behavior there. Now, to determine intermolecular force, you are often going to have to draw these substances. Now, if it's just carbons and hydrogens are London dispersion only. And it's London dispersion with a small molecule, so not very significant. With oxygen, that's also a nonpolar bond, a nonpolar molecule, as is hydrogen. Nonpolar. So all of these have only London dispersion. Those are small forces that require them to be very, very close together to experience them. Now let's take a look at SO2. You have to remember how to do your Lewis dot structures. I have 18 electrons here to place. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and clearly that oxygen on the left is not satisfied, so you look to the center, or that's how I like to do them. Other people do their peripherals first. I do my center. It really doesn't matter. What's important here is that you notice that there is a single non-bonded pair of electrons. This is going to be an angular structure, and with that non-bonded electron there, and so it's going to have a permanent dipole moment towards that non-bonded pair of electrons. In other words, this is polar. It's going to experience stronger dipole-dipole intermolecular forces. And so if we talk about intermolecular forces, SO2 is also the winner. So based on all of that, SO2 is our winner. And personally, if I was writing this question, I'd put number 1, point number 2. Make it very, very easy for the reader to understand. Okay, real gases approach ideal behavior at low pressure, high temperature, or both. Explain these. I really did that earlier. Okay, so I'll do it. This is kind of talking about it in the opposite direction. At high temperatures, molecules have a high kinetic energy. If they have a high kinetic energy, that energy is available to overcome or resist attractive forces. Those attractive intermolecular forces. When we are at very low pressures, then that means there's not many molecules relative to the space. There's a lot of distance between the molecules. And when there's little distance, there's not much intermolecular force. Okay. Additionally, if there's a lot of distance between them, the volume of the molecule becomes much less than the volume of the container. That's the only way you can have a lot of distance between them. All right. One of the van der Waals constants, you do need to know the van der Waals equation. It is given in your formula chart, but you should be able to interpret that. And one of the van der Waals constant is associated with the boiling point. Well, for a substance to boil, if it's going to boil, it requires energy. And during boiling, during a phase transition, remember, it's using that energy to break. If it's an ionic substance, it's an ionic bond. If it's network covalent, it's a covalent bond. In the context of ideal gases, you're most likely talking about discrete covalent molecules with intermolecular forces. So discrete covalent molecules. I wonder if I spelled that right. Is that ETE or EET? Somebody can look that up and tell me. All right. But it requires energy to break intermolecular forces. And it is the van der Waals constant A that adjusts the pressure that accounts for intermolecular forces. All right, I'm hoping I have time for this one if I do it quickly enough. And hopefully I don't do it too quickly to lose you. This is a popular type of question. Can you identify unknowns? It's like a little bit of a chemistry CSI. So let's take a look at the first part. They give us some information. We have a compound, 3 compounds that all contain Q. And these are their percent Q by mass. And then we're given some molar masses. And so we're just going to answer some questions. So now it tells me that the vapor density of X at 27 degrees Celsius and 750 millimeters of mercury is this. Calculate the molar mass of Q. Well, when I see density, and you know, molecular weight, this is probably a very, very old question. Molar mass is the term I tend to use. I like to use the meow-meow equation. Remember, cats put dirt over their pee. And that's when I tend to like to use this one. There are other ways you can approach this. Right? You can assume 3.53 grams and 1 liter would be another way to do that and plug into another form of the ideal gas law. But this is what comes to my mind, so that's how I'm going to answer it. I'm sure you can look up the official AP answer. So the density was 3.53 grams. 62.4 is R because we're dealing in millimeters of mercury. The temperature is 27. Don't forget, you have to embrace Kelvin when you talk about temperature, and it's rather as opposed to a delta T. And then I have 750 millimeters of mercury. And when you solve for that, I got 88.1 grams per mole. So now we know that this is an 88.1 grams per mole. All right, let's take a look at the next part. B says determine the mass of element Q per mole. Okay, well, I can get the percentage based on, I can get the amount based on the percentages given. So I've got molecule X, I've got molecule Y, and I've got molecule Z. We just determined that the molar mass was 81 grams per mole. Now remember that a percent is intensive. And intensive means doesn't depend upon the amount. So I'm just going to deal with 1 mole, which is the molar mass. And I'm going to multiply that by the percent as a fraction form. And I find that it must contain 57.1 grams of Q. And if we do the same thing with the others, this had a molar mass of 104 times its percent as a fraction, of course, and I got 75.9 grams of Q in this 104 grams. And for Z, it's 64 times 0.593. And that's per mole, so that's per 1 mole. So that's how many grams are equal to 1 mole of X. So it's a mass to mass, you know, within, sort of, is a way to think of it. And that's per 1 mole of Y. And then for Z, it's 38.0 grams of Q. Okay? So that is that question. That's all it asked us for. How many grams are in 1 mole of each? Well, 1 mole of each weighs its molar mass. Then you just multiply by the percent mass. Now this next one takes a little bit of intuition. It asks us, what's the molar mass of Q? Well, remember, these were on per mole basis. So what's the most probable atomic mass? Well, I look at 38, and it's the smallest number. And it roughly goes in evenly to Q, right? It's 2 times in Y. But it doesn't go in evenly for X. So that's not the lowest, the smallest number. So what we're looking for is the smallest number, the smallest common divisor, maybe that's what it's called. I'm just going to spell it out because I forget my math terms. Smallest number that divides evenly into 57.1, 75.9, and 38. So it's not 38 itself, so let's try half of 38. Half of 38 is 19. And we find that we do get an integral number for each of these. This is 2, this one is 3, and this one must be 4. Okay? And therefore the most likely number is 19. All right? So that's how we found the integral number. So it takes a little bit of mathematical intuition in a sense on that. All right, now this next one is a combustion problem. And I think I'm at about 15 minutes. I forgot to set my timer, but I'm pretty close. And this is a rather long segment. So I'm going to leave this segment for the next video, and we will continue our AP questions until then. So until then, this is signing off.